Hey, hello ib1 students. Next lesson about ideal gas. We'll be talking today more about ideal gas, about Clapeyron's equation, but at the very beginning, let's check your homework. If you didn't do your homework yet, please stop video now and do this for exercise from your circles, exercise number 13, 14, 15, and 16. Okay, I'm going to present a method, maybe not full solution, but just a method how to find it. Okay, calculate the number of molecules in 28 grams of hydrogen gas, which has a molar mass of 2 grams per mole. Okay, so first of all, by simple proportion, you have to find number of moles. If 1 mole has a mass of 2 grams, this is the meaning of molar mass, then how many moles you need to cover 28 grams? Of course, the number of moles in this particular situation is 14. So we have 14 moles of a gas. And how many molecules? Number of moles times Avogadro constant is number of molecules. Remember, Avogadro constant is given in your data booklet. So by multiplying this times this, you have solution. And this is the answer for exercise number 13. Okay, check. And exercise number 14. Calculate the number of moles in 6 grams of helium gas, which has a molar mass of 4 grams per mole. It's easier than previous exercise. Okay, we know mass 6 grams and we know molar mass 6 grams per 4 grams per mole. What does it mean? It means that 1 mole has a mass of 4 grams, and how many moles has a mass of 6 grams? Of course, answer is 1.5, and this is the answer, final answer for exercise number 14. 1.5 moles has a mass of 6 grams. Okay, easy. Maybe something more challenging. Exercise number 15. In exercise number 15, you have to find the number of moles in a sample of gas that contains 2 times 10 to the power of 24 molecules. Okay, so number of moles is number of molecules divided by Avogadro constant, so it's not challenging. Substitute, Avogadro constant is 602 times 10 to the power of 23. By dividing, you have number of moles. Answer for exercise number 15. Okay, and last one. Exercise number 16. I hope it will be more challenging because till now the exercises are extremely easy, like for middle school or primary school, not for IB physics students. Okay, determine the mass in grams of carbon of molar mass 12 grams per mole that contains as many molecules as 21 grams of krypton of molar mass 84 grams per mole. So first of all, you have to find number of molecules in krypton. We have krypton, which has 21 grams. We don't know the number of molecules. And we know that molar mass is 84 grams. So what does it mean? 84 grams is 1 mole. So by simple proportion, you can find number of moles of krypton. Okay? So number of moles of krypton will be 21 over 84. Okay, so this is number of moles of krypton. I'm going to use n with index of k. And how many molecules of krypton? Number of molecules of krypton is number of moles of krypton times Avogadro constant. So if you know number of krypton, number of moles of krypton, you can calculate number of molecules of krypton. Okay, so now we know we can start second part of the exercise. Determine mass in grams of carbon, which has molar mass of 12 grams per mole, and we know number of molecules. So number of molecules of carbon is exactly the same as number of molecules of krypton, which is given, which was calculated here. So how to find mass? Mass is molar mass times number of moles, because number of moles times molar mass, which is mass of 1 mole, results in total mass. So you have to find a number of moles of carbon, okay, because molar mass is given. So number of moles of carbon, Nc, let's write Nc. Okay, number of moles of carbon is number of molecules of carbon divided by Avogadro constant. Number of molecules is given, Avogadro constant is given, so also in an easy way you can find number of moles of carbon. Okay, more challenging, I see there is a less difficult method, easier method than presented by me. If you are interested in different method, please stop for a moment, think this exercise and solve it by using a little bit different method. Okay, you can write a new topic. I hope you are prepared. You have pen, pencil, etc., etc. So you can write a new. Still, we are talking about ideal gas, or new topic, or next point, Clapeyron equation. This is main equation, which is related with ideal gas. By using this equation, you can solve problems related with ideal gas. Okay, to find Clapeyron's equation, let's focus on three laws called ideal gas laws. Okay, so point number one, ideal gas laws. And as a first bullet point, first law is something known as a pressure volume law. You have this in your Tsokos on page number 129. So the pressure volume law. Okay, the pressure volume law is about the relation between pressure and volume of the gas. So what happens with the volume of the gas if pressure changes and vice versa. Okay, here in your Tsokos you have a design, a setup or apparatus of this experiment. So let's look. Let's imagine that there is a pump which is able to change the pressure, okay, of the gas which is confined in this pipe, and here there is a kind of a liquid which is able to compress a gas. So in other words, pressure is changed by a pump, okay, and the liquid compresses or decompresses gas. Volume of the gas can be found by using a reading of the scale. Okay, so if bigger the pressure is, then gas is more compressed and volume of the gas changes. If less pressure is, gas is decompressed and volume of the gas increases. Of course, we have to assume that temperature of the gas is constant. So we have pure relation between pressure and volume. And what is a result of this simple experiment? If you will plot how pressure depends on the volume of the gas at constant temperature, then you can obtain straight line, but relation is 1 over V, which means that pressure is inversely proportional to the volume. Okay, so pressure versus volume versus reciprocal of volume creates a straight line at constant pressure. What does it mean? It means that you can write this mathematically, that pressure is inversely proportional to volume at constant temperature. Okay? And this is something which is known as a pressure volume law. Please copy this to your notebook. It's very, very important. Stop video for a moment. When you will be ready, then turn video again. It will be another law called volume temperature law. Okay, so bullet point number 2. Volume temperature law. Okay, so this is about the relation between the volume of the gas and temperature, absolute temperature of the gas when pressure is constant. So pure relation between volume and temperature. on SOCOS on page number 131 you have apparatus needed to do experiment related with this law. Okay, so let's look. We have a bath. You can change the temperature of water in this bath. You have thermometer, so you can read temperature of the bath. Okay, and you have again a gas which is trapped in the glass and is covered by sulfuric acid. Okay, so what happens when temperature of the bath changes here? Then of course temperature of the gas changes, and due to the change in temperature, gas changes volume. If temperature increases, then volume of the gas increases. If temperature decreases, then volume of the gas decreases. Okay, so what is a relation? If you will plot a graph how volume depends on the temperature, you will obtain a relation volume versus temperature. You will obtain a linear relation if temperature is expressed in degrees Celsius. Okay, then of course for 0 degrees Celsius gas has a certain volume. But if you will elongate this line, and if you will find the point when this line crosses x-axis, you can read the minimum possible temperature, which in Kelvin scale corresponds with which in Celsius degrees scale corresponds with minus 273 degrees Celsius. In Kelvin scale, this temperature means 0, absolute 0. So when you will plot a graph how volume depends in temperature expressed in Kelvin, not in degrees Celsius but in Kelvin, then volume is directly proportional to the temperature in Kelvin scale, which means that line crosses the origin. Okay, so how to write this relation? Volume is directly proportional to absolute temperature in kelvins if pressure is constant. So this is second law related with ideal gas. Ideal gas volume is proportional, directly proportional to the temperature expressed in kelvins at constant pressure. Okay, please copy this, including scheme of apparatus. Okay, stop video, copy this, when you will be ready, turn it back, and it will be about third law. Okay, third law related with ideal gas is described on page number 133 near SOCOS. This the name is pressure temperature law. Okay, pressure temperature law is about the relation between pressure and temperature if volume is constant. Okay, in your SOCOS on page number 133 you have apparatus, scheme of apparatus needed to do this experiment. Okay, so let's describe it. So let's look. We have to check what happens with pressure if temperature changes. So again we have a bath. Okay, again we have a bath. Yeah, when you can change the temperature. Okay, you have a thermometer which is able to measure temperature of the bath, and there is a gas here, air, confined in the glass sphere, in this case sphere in glass cylinder, which is covered, which means that pressure of the gas, the volume of the gas is constant. Gas cannot expand, gas cannot be compressed because the volume of the cylinder is constant, and there is a pressure gauge, so device which measures the pressure of the gas in this container. Okay, and what is the result? Okay, if you will plot a graph how temperature depends on the how pressure depends on the temperature in degrees Celsius, then you will obtain a straight line, okay, but of course at 0 degrees Celsius gas has a certain pressure, okay. If you will elongate this line should cross x-axis at minus 273 degrees Celsius, okay. So what does it mean? At absolute zero. If you will plot the same pressure versus temperature but in Kelvin scale, then of course you will obtain a linear relation which crosses the origin, which means that pressure is directly proportional to the temperature in Kelvin scale. And this law is called pressure-temperature law. So pressure is directly proportional to the temperature expressed in kelvins if volume of the gas is constant. Okay? So we have three laws. How pressure depends on the temperature, how volume depends on the temperature, and how pressure depends on the volume. So let's write these three laws on one page. Stop video for a moment, copy this, and next slide I'm going to connect all laws in one equation called Clapeyron's equation. So point number 2, ideal gas equation. Okay, so first law was related with relation between pressure and volume. So you wrote that pressure is directly proportional to 1 over volume if temperature is constant. Yes? Second law was related with volume and temperature. Volume is directly proportional to the temperature in Kelvin if pressure is constant. Okay, and third law we are talking about is relation between pressure and temperature. And pressure is directly proportional to the temperature if volume is constant. Okay? Combining these three laws together, you can write that P times V over T is constant. Okay? PV over T is constant. This is the combination of these three laws. And what is this constant? This constant depends on the number of moles of the gas. And this constant is N, number of moles, multiplied by another constant called gas constant. Gas constant has a symbol of R, and the value is given in your data booklet and is equal to 8.31 in standard units, but let me check, it should be given in your SOCOS. Blah 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 blah. Where is it? Yes, 8.31 joules per Kelvin per mole. Okay, this equation can be written in a little bit different form. P times V, so pressure times volume, is equal to nRT, number of moles, gas constant times absolute temperature. And this equation, PV equals nRT, is known as an ideal gas equation, or Clapeyron equation. Okay, please copy this. When you will be ready, I'm going to change the slide. Okay, so again, what is ideal gas? Ideal gas is one which obeys equation PV is equal to nRT for all values of P, V, and T. So again, P is a pressure in pascals, V is a volume in meters cubed, N is a number of moles, R is a constant, which is equal to 8.31, and T is temperature in kelvins. As an ideal gas equation, or Clapeyron's equation, or equation of state of ideal gas. This is also very, very popular name, equation of state, of course, of an ideal gas. Okay, so remember this equation because this is the most important part of this chapter. Okay, so let's do 2, 3, 4 examples related with this equation. Okay, so open your Tsokos on page number 136 and let's do example 3.13. Okay, 3.13, this is our example. Okay, estimate how many molecules there are in a gas of temperature 320 kelvins, volume 0.0.25 meters cubed, and pressure of 4.8 times 10 to the power of 5 pascals. Okay, we can assume that this gas is an ideal gas, so we have equation PV equals nRT. P is given 4.8 times 10 to the power of 5. Volume is given 0.025 meters cubed is equal to N is unknown, R is a constant 8.31, and temperature is given 320 kelvins. Remember, it must be expressed in kelvins. So by using this expression, you can find N, so number of moles. The question is about a number of molecules, so how many molecules? So number of molecules is of course number of moles times Avogadro constant. Avogadro constant is given, so you can multiply number of moles times Avogadro constant. Clear? Okay, so let's do one more example. Maybe this one, 3.15. Okay, example 3.15. A fixed quantity of gas of volume, pressure, and temperature expands to a volume and pressure. Calculate the new temperature of gas. So we have two states. First, we have a gas at given volume, at given pressure, and at given temperature, and then something happens with these quantities related with gas. We have new volume, we have new pressure, and we have to find new temperature of the gas. Okay, again, we can assume that this is ideal gas, and for ideal gas we have equation PV equals nRT, or in this particular exercise it's better to write it in the form PV over T is equal to nR. Number of molecules of this gas in this exercise doesn't change, so right hand of this equation is constant. So we can write that PV over T is constant, or if we have two states, then we can write this with index 1 before and 2 after. So P1 V1 over T1 is equal to P2 V2 over T2. P2 V2 T2. Okay, so let's look. We know pressure 3 times 10 to the power 3 times 10 to the power of 5, yes. We know volume 3 times 10 to the power of minus 3. We know temperature 300 kelvins, remember temperature in kelvins, is equal to new pressure 6 times 10 to the power of 5 times new volume 4 times 10 to the power of minus 3 divided by new temperature. There is only one unknown in this equation, temperature of the gas after changing the pressure and after changing the volume. Okay? So please copy this And now let's do one more exercise. Open your Tsakos on page number 140. Okay, 140, and try to do with me exercise number 17. Page number 140, exercise number 17. Okay. Bottle contains air at 22 degrees Celsius and pressure of 12 times 10 to the power of 5 pascals. The temperature is raised to 120 degrees Celsius. Calculate the new pressure. Okay, so let's look. This is a glass bottle. Glass bottle doesn't change the volume, so we can say that the volume is constant. So this equation PV over T is constant. If volume is constant, can be written as P over T is constant. Okay, so old pressure divided by old temperature is equal to new pressure divided by new temperature. Is it clear? Volume is constant, so it can be written as P over T. P1 over T1 is equal to P2 over T2. Okay, so what do we know? We know the pressure before, so it's 12 times 10 to the power of 5, and temperature before, but remember, temperature must be expressed in kelvins, so to degrees Celsius scale you must add 273. Is equal to P2, which is unknown. The question is about calculate new pressure. The question is about new pressure divided by new temperature, and the same temperature must be expressed in kelvins, so you have to add 220 degrees Celsius 273, and you have equation when there is only one constant, unknown P2. Please stop video for a moment, copy this, solve this exercise. When you will be ready, watch the end of the video with your homework. Okay, so what is your homework? Your homework is, of course, Tsakos. So again, page number 140, you have to do exercises 18, 19, 21, and try 22. 18, 19, 21, and 22 try. Okay? So, watch this video again, make very precise notes. As I said, this is very important topic to you. You have to know these three laws, you have to know this Clapeyron equation, and you have to know how to use this equation. And remember, temperature in the equation must be expressed in Kelvin scale. Okay? Thank you for watching, and see you next time. Good luck!